reorganize, and that was because of the holidays. Obviously, no one wanted to attend a meeting right after New Year's, so we planned it a little advanced instead. So for the year of 2021, we have a lot of different speakers who are coming up. And first one being Shirley Meng, which is today. February, we have Chen-Shu Wang, and we'll have a whole bunch of great speakers in the future. Currently, we're booked out till June, but we have a few more speakers lined up for the months afterward as well. So I had an introduction slide for Dr. Meng herself, but I think due to time restrictions, we're just going to go on to it.
Mm-hmm.
Okay. Thank you so much for coming.
It's my pleasure. Thanks, Jason, for inviting. And I am very honored that Professor Mansren is also in the audience. Just for the students to know, okay, back in year 2005, when I was a rookie fresh graduate student, just got my PhD, Professor Mansren is the first person in the field who gave me a job interview. I would always remember that. It's really a great, my first job interview is with UT Austin. So, okay, let me dive direct.
I want to say that we missed to hire you. I think about that almost every day.
Yeah, fortunately, I was able to keep the collaboration with RAM for the last decade. So it's really a great privilege to actually keep the connection with UT Austin. And as I said, you guys is going to be one of the centers for the electrification, for the future of the advanced manufacturing for battery industry in US. So I hope my talk today is in some way, to make sure all the students are fully engaged in this exciting period of time and work very, very hard to enable that. Okay, so I think you can see the full screen, right? Yeah. Okay, so I will actually start my talk just to put everybody on the same page. There are plenty of batteries to be made. Okay, so if anybody tell you, oh, solid state is going to replace lithium ion, no. If you look at the history of batteries, right? When we have lithium ion batteries, did we eliminate lead acid and nickel metal hydride? No. All we did is to enable new applications. We have many emerging new markets, particularly in the flying cars, drones, planes, large-scale grid storage. And just to think about the population on the world by 2030, and think about the smart tablets, think about all the electrification of the cars, there are plenty of batteries to be made. So in terms of the Tera-scale energy transition, I hope everybody is on the same page that we need better batteries. Even though lithium ion is already doing quite well, we need more because the world needs more efficient electrochemical devices for reduce the greenhouse gas. So before I forget, I do want to thank all the students, postdocs, collaborators, and more importantly, the funding sources, Department of Energy. I think some of the work I show later on sodium batteries are actually funded by NSF in collaboration with Shell Corporation. We also have a very close relationship with LG Chem. And of course, both Professor Ram and I are Battery 500 consortium members. So some of the work I present is going to has something to do with the work did in consortium. So I guess, for the outline, there's 5 things I want to cover. I hope I, don't run out of time. I want to emphasize the importance of the new tools, characterization tools, and the calculation methods. The reason is because many students are, like me, 20 years ago when we entered the field of material science and engineering, you ask yourself, why 40 years ago the problems our pioneering scientists could not resolve, we have a chance now. So I hope I showcase the reason we can do it now is we have better tools now. And we have a better ways of characterizing things, predict things, and making things. And I will go through the story about the current status of the lithium metal batteries, briefly cover the cobalt-free cathode development. And then I think like Stephen asked in the beginning, I will talk a little bit about the reality versus hype in solid state. And last but not least, if I have time, I would like to emphasize the importance of going beyond the lithium ion. So intercalation chemistry has won the Nobel Prize. I think, I won't waste a lot of time to go through the details of intercalation, but, for students to start this field of research, in the early days, I said I treated the batteries as a person. The reason why I put all the fancy tools on the battery is because like a person, if you're sick, you have to get diagnosed, right? So a battery, if you shine an X-ray on the battery, you see the peaks shift, and sometimes one peak become two peaks. So that's a phase transformation, and the process has to be reversible. So one of the important things for developing characterization tools is that we have dynamic phenomena in the batteries. So when the batteries are operating, it is converting in back and forth chemical energy to electric energy, and this process is dynamic, and you are moving matters. That's the fundamental difference between batteries and the supercapacitors. In capacitors, you only moving the charges, right? And if you're moving lithium ions or sodium ions or zinc ions, you're moving matters. So therefore, this process, if it goes through a few thousand cycles, the materials will go through fatigue. Just like airplanes, go fly up and down, many cycles, materials will fatigue. So if you have lithium going back and forth for 1,000 cycles, you do experience fatigue. And how materials engineering or material scientists can come out with ways to make batteries last for tens of thousands of cycles, that's a materials problem, can be solved. There's no thermodynamic limit why we cannot make a batteries last for 10,000 cycles. Okay. So throughout the years, most of the research I do actually is pretty fundamental. We actually using X-ray, neutron, electron to look at the materials at atomic level, particle level, secondary particle level, and then when you cast it on the electrodes, you study the electrodes, right? So as many people now fully comprehend the level of complexity in the battery making, I want to also say the fundamental difference between battery and a fuel cell is battery is a thermodynamically closed system. It's very easy to understand if you just look at your cell phone. This is fully enclosed, right? So matter cannot go in and go out. Think about the fuel cell. Think about the combustion engines. The fuel comes from outside, get converted here, and there's matter moving out. So in the batteries, it's not the case. You only have lithium ion gets shuffled between the two electrodes. So for a thermodynamically closed system, this is so important to have the advanced characterization tools to understand at each step what inefficiency process is, where is the loss of active lithium. Because if you don't do that, if the device has only, let's say, 99% efficiency, the capacity drop very quickly, right? So sometimes we call it the power of compound interest rate. If anybody paid a mortgage, you understand, like it's really, really the compound phenomena of this efficiency loss can quickly deplete the available lithium for electrochemical cycling. So this is the reason why when we do characterization, it's very important for us to understand at each step what happened, and more importantly, we need quantitative. And the reason why we need quantitative is because you need to actually capture all the inefficiency loss. So all these tools are only available in recent decades, right? It's not available, say 20, 30 years ago, 30 years ago, you don't even have those advanced microscopy that can actually capture atomic resolution of lithium metal, which I will show you later. So all of those tools are the major differences that we are experiencing today as a researcher that in the early days are not available. And the underlying material science question is really the interface challenge, right? I have this quote say, whoever control the interface control the batteries. So the interface in the batteries is one of the most important parameters to control. And when we actually do batteries, we already mentioned that there's chemical energy, electrical energy, and then one need to realize when we're moving matters, okay, that volume change will happen. So there's a mechanical aspect. And more importantly, nowadays, people want fast charging. So if you do fast charging, moving matter very quickly, and because it's a thermal, it is an electrochemical device, right? So there's always the thermal effect. So all these different coupled phenomena needs to actually come together and think about how you can have a characterization platform that will able to capture all these phenomena in the battery. The other very important tools, actually, I did my PhD with Professor Gerben Seder, who used to be in MIT. He's a computational person. So I want to say that, many students now heard about, machine learning, AI, yes, all these computational tools, including this first principle calculation to calculate materials, voltage, and capacity versus lithium, it's really important. Why? Because if you look at how this is grouped as in all the known oxides, phosphates, borates, silicates, sulfates, right? These are known materials. Of course, there are students who are very brave. They will make new materials that never appeared in the database. But I just want to remind you, history tells us any new materials from actual discovery to the market takes more than 15 years typically. Just think about first time lithium iron phosphate made is 1997, okay? And then it takes a decade, more than a decade, and that's already very fast, okay? But now with the, of course, if we face a existential threat like the COVID, the vaccine can be developed within 2 years. So I hope that the climate crisis is so big that actually it enable us from materials discovery to actual applications in less than a decade will happen more often. But all these materials, known materials, for my own career in the last 12 years, for high energy materials, if I'm not making any new materials, I'm just utilizing what's already in the database, there's only a few materials we need to focus on. And that's the beauty of computation prediction, because you can actually screen out things, because you can try to study some 6-volt materials, but there's no electrolyte available. So we'll leave it there until we know there's some electrolyte that can be stable up to 6 volt. And then we can go and unlock those materials for the application in the battery. But for now, some of these materials, as you see, they're all oxides. These oxides are definitely worth studying and should be focused on. And some of the cobalt-free materials is actually in this region. Okay. Now, what have the field done in the last 20 plus years? I think it's truly exciting. We're somewhere close to here now, right? And of course, this figure is quite old, but I want to emphasize we use this roadmap since 10 years ago. Why roadmap is so important? Because the field as a whole has a commonly agreed way of assessing energy density, both volumetrically and gravimetrically. And how all the metadata behind this graph is very, very important, right? Regardless, the field has a consensus how we evaluate. And then in the last 20 plus years, the battery energy density has been more than tripled. You don't feel it because your phone performed 10 more functions 10 years ago. But in a fixed 18650 cell, when I was a student, we're getting something like 2 amp hour. That's in the early 2000s. Today, I can easily get a 3.5 amp hour 18650 cells. And that's the progress. Now, we can actually, the cost reduction, China definitely should be credited for helping the 10 times cost reduction for the batteries. Also, today, I think a cycle life for a few thousand cycles is not a problem. And I think everybody knows 10 times growth is expected in the next few years. I think this number is already outdated. I mean, we're probably approaching 200 gigawatt hour production per year, right? So I guess in a few years, you're going to see terawatt hour production per year. And recycling and reuse is a very important topic. I hope all the students in the future, when you design new battery chemistry, recycling should be actually in the design parameter to think about how the lithium-ion batteries will be recycled. So according to our assessment, by 2026, when the first generation electric vehicle retires, the recycling will become one of the major topics in the world. So everything we see here, the achievement, is enabled because the breakthroughs in fundamental material science and engineering, from the cathode moving from cobalt rich to nickel rich, and perhaps in the future sulfur, to anode from graphite to silicon, and then actually battery 500 bypass silicon went directly to lithium metal. And then all these electrolyte, I think the electrolyte development is so exciting for this discovery of new battery chemistry. So the development of lithium metal batteries is not brand new, right? So 1970s, when Dr. Whittingham's first paper in Science, 1976, he used a thick block of lithium metal and titanium disulfide as the cathode, right? Now you look at how that time the lithium metal battery looked like to today, the lithium metal batteries we are working on in the Battery 500 consortium. One thing immediately jump out is that the thickness of the lithium metal. Because in the cathode discovered back in the 70s, the cathode does not contain lithium. So you need a lot of lithium in the anode. However, today, with LFP, lithium cobalt oxide, nickel-rich NMC, we have plenty of lithium on the cathode side. So we don't need a lot of the lithium on the anode side. And lithium is light, but actually occupies a lot of volume. So this is the reason why that we target the lithium metal as the crown jewel for these, going for high energy density. And visually, you can actually see, in the past, because of this thick block of lithium metal, people always worried about the dangerous nature of reactive lithium metal, right? So this is, I think, the main motivation why lithium metal is so interesting. And of course, if you enable the lithium metal, naturally people will think, can you actually enable sodium metal? I have no answer for that, but I would say that sodium ion batteries always are blamed for low energy density is because sodium metal cannot be utilized. Okay, so lithium metal, to look at the lithium metal is not an easy task because lithium reacts with everything. When we say everything, it means everything, okay? So lithium reacts with oxygen, nitrogen, reacts with CO2, water, and it can alloys with many, many metals. So one of the things we first discovered why it is so important to have the right tool to look at the lithium is because one of the tools we have called the focus ion beam, using gallium to cut the cross-section of the lithium to look at the lithium. And then when we use the room temperature cross-section view, we found that this lithium alloy with the iron source, the gallium. So everything we measured here is the lithium gallium alloy instead of the pure lithium metal. Now, one of the things that the Thermo Fisher Scientific help us to do is to build a cryogenic stage that you actually, the sample does not see the liquid nitrogen, but we can pump the liquid nitrogen, cool down the stage, and we can significantly reduce the kinetics of the lithium gallium alloy, and you can actually get the form, like the right pristine form of lithium. So this tool is so important because then you can actually evaluate what effect of engineering strategies have on lithium metal. So if you just use the traditional carbonate electrolyte developed for graphite to deposit a lithium anode, you get this kind of very, very porous. That people call it dendrite because it's just the whiskers looking, and it looks like dendrites. And when we actually change the solvent and the salt, now we have a very effective tool. You can actually look at the three-dimensional tomography of the lithium deposit. Obviously, when you change the solvent and the salt, the crystal size and everything of the lithium is very different, right? So this is give us a way to properly measure if you did modify this electrolyte, if you did modify things, where is the actual phenomena you see. On the other hand, cryogenic TEM is also very important because we always have this imagination. Okay, SEI is the biggest problem for lithium metal because you grow this interface and the lithium metal is consumed by the SEI. And it turns out, if you don't use the cryogenic imaging, because you see these lithium metal are completely encapsulated in the SEI. So the SEI contains lithium oxide, lithium fluoride, lithium carbonate. They're very insulating. So when you do room temperature imaging, these compounds will be so unstable that you can't really make the actual observation. The materials is just unstable on the E-beam. Now you have a way to stabilize it. So when you look at the cryo imaging, you see this is a conventional electrolyte. Really, the morphology of the lithium grown is whiskers, right? If you change the electrolyte to ether-based electrolyte, they really are the large granular crystals. And then the SEI, this SEI here, you see in the whiskers shape, there's a lot of these metallic lithium that are encapsulated inside the SEI, right? So from our observations, we really do not see any components difference in the SEI between the new electrolyte and the old electrolyte. So then Chen, my student now, the assistant professor in Michigan State, we find, let's go and quantify how much metallic lithium is actually left there. So it turns out all the SEI components can dissolve or react with water to generate methane or CO2. Lithium metal is the component that will generate hydrogen. So we build something using titration gas chromatography to basically titrate out this metallic lithium and measure the amount of metallic lithium in the whatever current collectors or the substrate that you have. So it turns out after we use many different types of electrolyte, they all have different capacity loss, different coulombic efficiencies, we can actually see that the metallic lithium, the one that encapsulated the SEI, correlates perfectly with the capacity loss. Not the SEI, actually the SEI amount is almost identical. The composition and amount is almost identical. So this back a couple of years ago discovery is so important to realize the low efficiency is mostly caused by the lithium contact loss of lithium, right? So if you have very tortuous microstructure, you can actually run into the situation where the electric pathway is cut off. So those lithium become electrochemically inactive. But if you have large granular crystals, you actually run less into such a problem, right? So naturally, because this microstructure phenomena, we think, okay, what's the best way to ensure that the contact is very good? So that actually lead us to propose three things. Like one is, of course, you need the electrolyte where the nucleation site, it always nucleate large grains instead of these kind of tortuous whiskers type of lithium. And you can also, of course, the artificial SEI is an important concept. 3D carbon collector is an important concept, but those execution is really, really difficult. So instead, we focused on using pressure as the other knob to control the lithium metal deposition, because we figured the lithium's is so soft at room temperature. Lithium, you can easily use the pressure to manipulate the lithium crystals. And it turns out the lithium metal can be manipulated with reasonable amount of pressure, only 300 to 400 kilopascal. That's not a very high pressure values. And then you can see the lithium deposit. These are 2 micron scale bar, right? So we're depositing very thick lithium, and you can see, almost the perfect columnar structures of the lithium can be deposited and reversibly, right? The most important part is how you can strip those lithium and deposit it back. So I think through this exercise, pressure control becomes such an important parameter. So it's implemented in the pouch cell development. So this is the consortium's data release. You can see 2020 data hopefully will be released very soon. And we're really, really making huge progress. And this is where the protocol battery 500, this is multi-layer pouch cells, so important to release these data to show where we are today for the consortium, right? So I think the other story I want to say is that, the electrolyte is so important, right? So my school, my group actually invented this, we call it liquefied gas electrolyte. I think Cyrus Rasmaji was my postdoc who proposed a crazy idea using the fluoromethane gas as a electrolyte that under high pressure we can liquefy. So if we do the electron affinity and ionization test, this is a totally crazy idea, okay? Because I've never thought, as a professor, I've never thought using gas as the electrolyte. But Cyrus convinced me. He told me, Shirley, ethylene carbonate is actually EC is actually a solid, right? That didn't stop people using ethylene carbonate, because if you combine ethylene carbonate with linear carbonate, it becomes liquid. So the goal here is that he used the pressure as a knob. He can liquefy this gas molecules, just like your barbecue tank. You can liquefy the gas. And then with that, we demonstrated the minus 60 C operation of the lithium metal batteries. And in the last 2 years, we've been very, very busy to redesign the composition of this electrolyte. Now we widen the temperature from minus 80 C to positive 80 C, and then utilize the concept of the localized high concentration electrolyte. Just like the liquid people use, we can utilize here with cold solvent like acetonitrile or THF. And the lithium we deposit here are really truly dense, even at minus 60 degrees Celsius. And this is the a quick story to show where we are for lithium metal. I really think lithium metal is very close to the actual prime time, hopefully in a couple of years. Now, whenever I talk about lithium, people always ask me my opinion about the silicon. I would say this is a literature review of the silicon, right? So target is here with very high loading of silicon and with very good cycling retention. It is in my opinion that without a good electrolyte, it's very difficult to be here. Okay, so I hope that with all these hundreds of thousands of publications in silicon, we're going to see breakthroughs in the coming years. Yeah, so I cannot review too much details here, but hopefully, we'll come back here, answer some questions if people are interested in knowing. In terms of cathode, still very important, because if you want to reach 500 watt-hour per kilogram, this is, again, battery 500, it should not be ASAP, it's already out for a long time. So if you want to reach high energy density, remember, lithium is in the cathode side, right? Because we're using very thin lithium foil on the anode side. So the cathode capacity needs to go up, right? 252 is a big number because most of the layered oxide cannot reach over 220. So lithium-rich layered oxide, as well as this high voltage cobalt-free and NMO. So I think UT Austin have worked on both materials very, very heavily over the years. I just want to say, we are very happy to work with UT Austin on the cobalt-free LNMO. We are moving along our target. Again, a literature review is so important because all these great retention cycling numbers, the loading is so low, it's really irrelevant for the battery industry, right? And where we want to be and where we can achieve, like we did achieve something with a very small circle, very low loading, but that's not counted, right? Because the target is you need the scale, 4 milliamp hour per centimeter square, and that's still quite a big challenge. The reason for that is because many of the new cathode materials require high voltage operation. So high voltage means that highly oxidative. Everything reacts with high voltage. Even the carbon, so these are different carbon we use, even the binder, different binders we use will impact the electrochemical performances. So now when we think about discoveries or development of new battery materials, if you go for high voltage route, you really have to optimize every component inside your cell, because at the high voltage conditions, the inactive materials may be one of the major contributing factors for the capacity degradation. So even for NMC cathode, if we want to push the voltage up, we have a lot of work to do, not on the battery cathode materials itself, but on the cell component, binders, carbon additives, separators. So I think this is the area, material scientists call it the materials at extreme conditions. It is extreme condition. I think a lot of people don't realize how oxidative it is for voltage above 4.5 volt versus lithium. It's an extremely oxidative environment. Okay, now I hope I don't run out of time, so I'll just jump to the solid state batteries because a lot of people ask me this question. So not targeting any particular startup companies. I think let's stay on the facts. Why we want to do solid state is driven by safety, the desire for safety and desire for sustainability. Why sustainability? Because we have a chance to redesign the battery for 100% recycling. So I think my colleague Zhen Chen and we already published several papers to say, if we want to do solid state batteries, let's do it in the 100% recycler battery way, because this is our chance if we are going to do a new battery platform. So the allure for solid state is very clear, because if you visit my lab, I have single pouch solid state, I'll let you cut the batteries, right? It's always magical when you actually can do that in person. And we can also put the battery on 200 degrees Celsius hot plate, it will work. So clearly the driving force for solid state battery, because the high volumetric energy density, you solidify everything. And you can actually abuse, has very low fire explosion risk, and can operate a wider temperature. And the assumption of wider temperature means less thermal management is actually false. It's not correct, but that's always how we wanted to champion for the field for solid state. Now, word of caution is really, we improve the performance, but how much cost do we perform? So whenever people talk about the battery price, what we actually mean is the cost performance ratio. Indirectly, you are implying that, right? So I want to say that today lithium-ion battery is doing so well. The cost performance ratio is something like $150 per kilowatt hour. Now, if we had a certain percentage of increase, really need to ask ourselves the cost. And for this reason, for Steven's question in the beginning, we really need, I will tell you at the moment, it's not even comparable for solid state to actually roll out this number. There's many reasons for that. I think I'll skip this. Let me first talk about how did you enable a solid state device. Okay, interfacial phenomena in liquid, the cathode and the anode are both stable, chemically stable in the liquid electrolyte. You see the HOMO-LUMO is so wide, and because we're using intercalation chemistry, right? So the anode is quite stable, cathode is quite stable, and then you actually form SEI. This is well established in our field. Now you start using solid, and the worst come worst is the solid that we want to do is lithium metal. And bad news, lithium metal reacts with everything, right? Even if it's a polymer, if it's a sulfides, they react. The only two solid electrolytes that's stable with lithium is LLZO and lipon, right? So you actually have a chemical stability problem. And the cathode, the only cathode we know is NMC or LFP, and NMC or lithium cobalt oxide, they are oxides. So if you put it next to a sulfide, they will react. So a lot of times, majority of the time, the people do is to do coating. Coating have to protect the cathode, protect the lithium metal. On top of that, you start electrochemical cycling. So the SEI come to play. And we wrote in this chemical review paper, there's so many interfaces. You don't even know where to start. Because in solid the liquid cannot flow, right? So sorry, the electrolyte cannot flow. So if you have a defect, a crack, that's a new interface because it's not, the electrolyte cannot flow. So this gives you huge amount of engineering challenge because yes, coating has to be applied. And there's lots of coating materials. Lithium niobate is not the only one. You can do phosphate, you can do borates, you can coat the cathode with the solid electrolyte. But just think about the price comes with those coating process, right? I think we did this boron coating. Boron is really quite a good light coating materials. You can do it, but I want to say all these cycling numbers here we showed you here. Critical current density is like 0.1 milliamp per centimeter square, right? So if you wanted to actually really cycle lithium metal in the solid state batteries, pressure effect also is unknown. I will tell you, we know so little about the lithium metal's mechanical behavior. It was a surprise to many people. Actually, lithium metal needs to be cycled at a relatively low pressure because the plastic deformation of lithium happens severely if you go high pressure. So for solid state devices with lithium metal as the anode, you cannot put 20-25 megapascal. You actually have to release the pressure in order for it to cycle. Again, the cycling current density is only 0.1. Okay, so I think what we are done today is in UCSD at least we can make solid state batteries without a drop of liquid, no liquid at all. Okay, and the applied pressure is 5 megapascal. We can actually cycle pretty well at 60 degrees Celsius. I'll tell you, we're nowhere near room temperature cycling with lithium metal. Hopefully, we will report very soon. With a different anode strategy, might be possible, but this is still only in the small lab scale test. Right now, I think in terms of the characterization challenge, I don't want to mention. I just said interface control is so important. Since I do want to spend some time to answer questions, I want to show you where I think we are in solid state battery development. In order to us to have a solid state batteries, we already resolved ionic conductivity. So there's multiple electrolyte, oxides, sulfides, halides. They have reasonable ionic conductivity, very, very close to the liquid. And remember, you don't need to have the liquid conductivity because in solid state, transference number is much higher. So you can actually live with 10 to the power minus 3. So that opens up a lot of electrolytes. Interfacial stability and mechanical stability, particularly mechanical stability, I feel like I just started understanding, okay, because of the lithium metal, you are in the solid state. There's so much fundamentals not understood here. Now, the next step is the processability and the scalability. I think for me, it's a big question mark. So far, the only materials that can have give me 1 kilogram scale is the aldehyde lithium phosphate sulfides with chlorine doping. That's the only one I can easily get a kilogram in quantity. None of this can give me the only things here, okay? None of the others give me kilogram less than $1,000, $2,000. Even for aldehyde, I'm paying $2,000 per kilogram, right? So we have a long way to go for processability and scalability. And I emphasize that if we have a chance, let's do it right with the right sustainability and the recycling ability. So with that, I think I come to the last topic is that there's still a lot of materials discovery in solid state. This paper hopefully will come out in Nature Communications soon. We still continue to discover new solid ionic conductor, this yttrium zirconia based halides for room temperature sodium conductor can enable very stable long-term cycling, 1,000 cycle long solid state sodium batteries. So new things are still being discovered, and new processing method I will show you, we can actually, with the zinc batteries, you can actually make flexible batteries. You can open up IoT, so those are the areas I think very exciting for all the new students who are coming to this field. You don't have to do lithium. There's sodium batteries for grid storage. There's zinc-based batteries for IoT, soft robotics. So I hope I touched all the important topics I want to share with you. And of course, nothing is possible without my brilliant students. This group photo is very old because I haven't seen them for 9 months as a group. So hopefully, the talk is helpful for all of you to think about the future of electrochemical battery research. Thank you very much.